Hello, everybody, and thank you for joining my webinar. I want to thank LGC for giving me the opportunity to talk about some of the cannabinoid separations that I've been working on in our lab. So the title of my presentation is Getting the Most from Your LC Cannabinoid Separations. My name is Connor McHale from Advanced Materials Technology, and I'm on the technical support team. I'm there to give you any type of column recommendation or method development advice. We'll just give you some more information on the products that we have to offer. So the presentation outline today, I do want to give a brief overview of the company Advanced Materials Technology. We'll go into the benefits of fused core particles for your LC separations. And we got a new stationary phase technology specifically for your cannabinoid separations. I also want to go into some of the method development that I faced for the cannabis, more specifically the potency test. And we'll go into some more details about our new Halo 1.5 millimeter ID column. After that, we'll go and review some of the technical resources from our webpage that can help you out for some of your chromatography in the future. So Advanced Materials Technology is located in Wilmington, Delaware, and we make everything right on site here. That being from the fused core, from the bonded shell to the actual stationary phase bonding, column loading, and the shipping and manufacturing. It is all done right here on site. Now, we are known worldwide. We have distributors from all over the world that sell our product. And we also have some local distributors from the United States as well. We are ISO 9001 certified, founded in 2005. So you might be asking, what is this fused core technology? And this is what AMT is really known for. If you could point your attention to the image on the left, this is a better known fully porous particle that has been around for quite a long time now. When you compare that to our solid core or your superficially porous particle, or better yet, SPP particles, you can see that on the right. You can clearly see a difference with this solid core in the middle of the particle. And you might be wondering, what does this do? Why do we care about this solid core? And it's quite simply that the sample diffusion path is going to be cut down significantly. That's going to allow you to get some sharper peak widths and sharper peak shapes. And not only that, you're able to bump up your flow rates and get some high throughput with these compared to your more typical fully porous particles. And we'll see some lots of chromatograms in this presentation, FPP versus FPP kind of separations to see why this really matters and how much of a difference it actually makes. Now, we do have solutions for all HPLC users regardless of their instruments. And what I mean by that is if you have some back pressure limitations, maybe you have some of the older HPLC instruments, we do have some larger particle sizes for you to choose from, that being the 5 micron. Now, if you have a UHPLC or some of the latest and greatest instrumentation, maybe you might be interested in our 2 micron particle size for your separations. Typically, as you reduce the particle size of your column, you're going to get some tighter efficiencies, but you're also going to get some higher back pressures. And of course, LCMS, all of our columns are LCMS compatible if you decide to do some of that. Now, when it's all said and done, this fused core particle design is really going to yield to faster and higher performance columns without the back pressure consequences, which is why a lot of people consider our product. So I do want to go over the AMT product portfolio. We have a lot of different products for your separation needs. I first want to start with our small molecule line. That's going to be on our 90 angstrom pore size at 3 different particle sizes, depending on your instrument back pressure limitations. So that's going to be the 2 micron, the 2.7, and the 5 micron on the 90 angstrom particle size. If you're doing some more bio work, whether that's peptide or protein analysis, we do have a solution for you. So that's going to be on some larger pore size material, such as the 160 angstrom, the 400 angstrom, and even the 1000 angstrom material. We also have an Enviro class that's going to focus more on the environmental applications, your real popular PFAS compounds out there, or whether you're doing some polyaromatic hydrocarbons, maybe you're doing some mycotoxin or pesticide analysis as well. We have lots of different applications and products specifically designed for that. Now, lots of different various chemistries that are going to give you differences in selectivity. And again, whether that's small molecule or large molecule analysis. Um, Recently, we came out with the new Halo 2.7 micron low pH C18. So this product is specifically designed for low pH applications. Product works great at pH, 3, 4, 5, but when you are operating at the extremely low pH range of pH 1 to 2, this stationary phase really shines, and that's because it has a sterically protected ligand, as you can see on the bottom left here. Now, compared to a standard C18 column, if you point your attention on the bottom right-hand graph, you are not going to be getting retention drift over time, and that's due to the sterically protected ligand. So if you're considering running your applications at really low pH and you're dealing with some column stability issues, this may be a product for you to consider. Now, later in this presentation, we're going to be talking about the cannabis potency test, and I've used all of these um, chromatograms using this column, and we found that it actually really benefits from the sterically protected stationary phase. We'll go into that here shortly. Now, the cannabis testing industry has been around for a while now, and as more and more of the regulations change, this is becoming extremely important. You'll see some news articles online of maybe the companies being sued over the potency of its joints, and whether that's intentional or by accident, I'm really not quite sure, but we'll go into some reasons on why it could be an accidental labeling on the package. From some of the studies that I've seen, this could definitely be a possibility, especially if you're just doing some UV or PDA detection. That being said, the more potent these products are, you usually see the price increase as well. So that has a really important role on the package labeling. So let's do a quick overview of the panel that I'm going to be looking at. You can see there's definitely a lot of acids in this potency mix that I'll be looking at. We're going to be looking at 17 different cannabinoids. Eventually, we're going to have a total of 18. And you can see at the bottom right the standardizing cannabis lab testing recommendations on which of these compounds to actually screen. Now we'll be looking at the majority of these, but I do want to point out some of the different properties, especially the acids. So if you can see in this Journal of Natural Products table, you can notice that the pKa values are right around 3, and that's going to play an important part on what kind of mobile phases we use, specifically the buffer and the acidic modifiers that we're going to use in our separation. So I did select formic acid and a combination of ammonium formate as my main mobile phase of choice. And you'll see here shortly why we chose that. But the formic acid specifically we chose because the pH range is going to be right around 2.8 to 4.8. And that's right where we're going to be operating at. So let's start by the samples that I'm going to be looking at. So these samples were sent to us from LGC, so I want to thank you again for getting these samples in our hands. You can see here the first cannabinoid mix that we're looking at is a total of 11 compounds. It's going to be a combination of acids and neutral compounds. You got a couple isomers in there as well. The reference material certificate can be seen at the top right here. And actually the bottom chromatogram is ran on our Halo low pH C18 column. So this is going to be the 2.7 micron 46 by 150 millimeter ID column. You can see we're getting some really nice baseline resolution here, especially between the isomers such as delta 9 and delta 8 THC. And this is an isocratic separation using a combination of ammonium formate and 0.1% formic acid. Now later in this presentation, I'll go into the method development and how we actually got to these conditions, but this is the first mix of standards that we're going to be looking at. The second mix is very similar. That's going to have, again, some your acids and neutral cannabinoids in here. This is going to be a total of 6 compounds. using the identical testing conditions that you saw in the previous slide. Again, you got the reference material certificate. I really like that LGC throws these reference chromatograms in their paperwork when you order the sample. Um, it, I thought it was kind of neat. You don't really see that with a lot of the different standard um, companies out there. So we'll go back to the stationary phase, and you might be wondering, is this just another C18 column? Maybe I have a C18 in my drawer. Can I just use that? And one message that I really want to emphasize is this is not just another C18 column. There is a reason why we came out with this stationary phase. And although they might look somewhat similar in terms of the C18 ligand, these minor differences in the stationary phase play a really important part in selectivity in the overall chromatography. So as a reminder, we currently have four different types of C18 phases for our small molecule product portfolio. You have your standard Halo C18 product, which is a great universal product. We actually have a lot of customers that use this for the cannabis potency test. We also have our Halo AQC18. This does really good with polar analytes. It's also 100% aqueous compatible, so if you have some really polar compounds and you don't have enough retention, you could consider running an AQC18 column. We all have our Halo polyaromatic hydrocarbon stationary phase. This is a trifunctional unendcapped C18. Really ideal for these polyaromatic hydrocarbons, which are neutral compounds. And then again, the Halo low pH C18, which is optimized for small molecule reverse phase separation, employing mobile phases with very low pH and elevated temperature for acidic and neutral compounds. Now, how do all of these compare in terms of the chromatography? So let's take a look at those two mixes from LGC. So here's a combination of both LGC mixes. That's going to be a total of 17 different cannabinoids. And what I really want to point out is that all of these columns show differences in selectivity, whether that's giving you baseline resolution between a critical pair you're looking at, some coelutions, you see some high tailing factors for some columns. And really, I just want to point out that they're all not going to behave in the same way, even though they have minor differences to the stationary phase. When you compare this to some other competitor columns on the market outside of advanced materials technology, you see the same thing. So here, again, 17 different cannabinoids, and we're comparing that with some other competitor columns on the market that are really known for this cannabis potency test. If I could point your attention to the chromatogram at the bottom, you can see here we have a fully porous particle material, and we're getting a significant increase in peak width. Um, the peak pairs with a red asterisk above it are actually coelutions, which I think are really important for people who are doing PDA and UV analysis, because if you're not running individual standards and you don't know where these things allude at, you could be integrating these peaks that are actually coelutions and doing a higher potency value than maybe expected. These are really important pairs, such as your delta 8, delta 9 isomers, that are extremely important when making the label for these products. So the importance of knowing where these things elute and that all C18 columns are not the same is extremely important. You can see here when we look at the column efficiencies for all of these columns, we're looking at the total of 17 different peaks, that there is a huge difference between the SPP and FPP products, and that is primarily due to that fused core particle technology. Again, that sample diffusion path is limited with the fused core, and that's going to allow you to have some tighter peak widths, which all in all turn to higher column efficiencies. So the next part of this presentation is more of the method development side of things, how I chose these mobile phases, how I decided to go to this particular pH, temperature, and the different stationary phases that we picked. Um, from there, I do want to talk about the acidic modifiers used. So if you run this panel with just water and acetonitrile, that would be extremely convenient and nice for everybody, but unfortunately you cannot do that. Based on the pKa's of these acidic compounds, you are going to have some type of acidic modifier in there. And that's exactly what you see at the chromatogram at the bottom here. We do a combination of ammonium formate and 0.1% formic acid in our water line, and you can clearly see the improvement on the peak shape, specifically for these acidic compounds. Now, keep in mind that you can put the acidic modifier in the organic line as well. Some people might not think of this, but you can clearly see a difference, especially if you have some acidic compounds in this panel. So the top chromatogram is just with acetonitrile in your organic line, and the bottom chromatogram is adding 0.1% formic acid to that. And what you see here is an increase of retention for your acidic compounds. Your neutrals pretty much stay the same, but your acidic compounds are going to be gaining retention, which is one, going to give you a change in selectivity, and it could give you some advantages in your separation, depending on what you're trying to do. Here it actually helped improve the resolution of critical pairs. The red asterisk over here at the compound A6 is actually a coelution. So as you throw the acidic modifier in your organic line, you're actually able to pull that apart. And this can be an extremely powerful tool as you keep adding different standards to this mix, and you have to make certain tweaks to the chromatogram, which we'll see here shortly. Now, don't forget about methanol. This particular mix, I decided to not use methanol in my final chromatogram, but methanol is a really powerful solvent. It's actually a greener solvent as well. Some of the things that methanol can do is, one, it's going to give you some higher retention. So if you're struggling with retention times, not enough retention, maybe some compounds are coming out of the void, methanol is definitely something to consider. On top of that, methanol is going to give you differences in selectivity. You can see some resolution changes here between some of the peak pairs, whether that's an increase in resolution or a decrease. Again, you're going to have the higher retention times. And interesting enough, you're actually getting a difference in selectivity for the first two peak pairs. So methanol should not be forgotten about. In fact, I always try to use methanol in some of the application work I do because you'll be surprised with some of the advantages it can give you. So, like I said in the previous couple slides, you validate a method, it looks great, you're really happy with it, it's nice and repeatable, but then a new cannabinoid comes up on the news, or maybe you have to screen for this particular one. So here's a little bit of a case study when we have exo-THC. And using the same conditions I showed you in the previous slide, when we run exo-THC, unfortunately, it coelutes. You can see that blue triangle is actually where the exo-THC comes out at. And that can be really a pain because you've done all this work for your cannabinoid separation, and now this new standard is showing a coelution, and now you have to reevaluate your whole method. Well, keep in mind the trend of the acidic compounds versus pH. And what I mean by that is as you increase your acidic modifiers or decrease your overall pH of the solvent, you're going to be gaining some retention times. So if we tweak that organic line, that's going to have your acetonitrile with 0.1% formic. We dial that down to about 0.05% formic acid. We're now able to alter the retention times of those acidic compounds and pull apart these peak pairs. And we can now see that exo-THC that was originally hiding under that main peak is now baseline resolved, and we're able to take a look at it. Now, if you look at that, now we have a total of 18 different compounds here with baseline resolution, and that is just by altering the mobile phase of your conditions. So I had a little bit of fun with this mix. We also offer the low pH C18 on our 2 micron product line. And I threw this on our triple quad. Now I'm not fragmenting these, but you can see the precursor ions and all the different isomers in this separation. This is on a shorter column dimension as well, so you're going to see some faster run times. Instead of the 4.6 by 150 millimeter ID, I threw this on a 2.1 by 100 millimeter ID column at the 2 micron particle size. Now we do have a new dimension in our product portfolio. That's going to be the 1.5 millimeter ID column. Now what this does is it's going to give you a boost in sensitivity, some higher ionization efficiencies from your LCMS systems. And one of my favorite aspects of this product is the reduction in solvent consumption compared to larger ID columns. If you have some Go Green initiatives for your company, this could be a very easy way to implement it. All in all, you're going to be using some lower flow rates, and as you're injecting throughout the week, your solvent consumption is going to be cut down dramatically. So now let's see an example using the new 1.5 millimeter ID column. The blue chromatogram here is on the standard 46 by 150 millimeter column, which you've seen chromatograms of that throughout this presentation. Moving that over to the new 1.5 millimeter ID, we can clearly see a boost in our sensitivity. Not only that, but our solvent consumption is cut significantly. We're actually saving about 9 times the amount of mobile phase, with about half the back pressure as well. Now, the bottom right chromatogram is that full mix of LGC. That's a total of 17 different compounds. And we're getting some nice baseline resolution using the 1.5. Now, one thing to keep in mind when you incorporate these 1.5 millimeter ID columns, the amount of dwell volume is extremely important, or you want to limit the amount of sample dispersion. And the easiest way to do that is you could swap out the tubing pre and post column. You can also reduce the flow cell volume and incorporate some zero dead volume fittings. But you want to reduce that as much as possible to get the most out of your column. I now want to talk about our technical resource page on our website. So that's going to be at halocolumns.com. The technical resource page is great. You can see all the examples I showed you today are going to be on there. We have lots of different single page application notes, previous conference posters, technical reports, white papers, all of our different brochures on our products. It's definitely something worth checking out. We also have a LinkedIn, a YouTube, and a Facebook. If you feel free to follow us on there. And with that, I'll take any questions. You can see we have our sales and technical and marketing material email, technical support, so I'll be part of that if you have any more questions about our products. And of course, if you have any sales related questions, you have the email up there as well. And with that being said, I also want to give a special thanks to LGC for supplying the standards. I've been really happy with them so far, and I look forward to some future work with you. Thanks, everyone.